Hello all, welcome to FISICA. Today we are going to discuss a new topic, Miller indices. So let's start. What is Miller indices? Miller indices are used to specify directions and planes in lattices or in crystals. Then the number of indices will always match with the dimension of the crystal, which means one index implies we are representing it in a 1D lattice or crystal. Two index means we are using it for a 2D lattice or crystal. Similarly, 3 index means we are using it in a 3D lattice or crystal. That is, number of indices will always match with the dimension of the crystal. Now, let's go for its notations, how we are representing this Miller indices. Let H, K, L are the Miller indices which we are concerned right now. Then, so this itself indicates that we are going to represent a 3D crystal or lattice. That's why we have used 3 indices, H, K and L. Now, H, K and L inside a parenthesis separated by comma is the notation for representing a point. So if we are representing 3 points, we used to write it inside a bracket with comma. Now, H, K and L inside square bracket will represent directions, which means if you are representing direction of a point from certain reference, you will be writing it as HKL inside a square bracket. And HK and L inside an angle bracket is representing a family of directions. So in the later lecture, you will understand what exactly a family of directions. But just not the notation. If you are representing it inside a bracket, it is a family of directions. Now, H, K and L inside a parenthesis will represent a plane. Please note that here we are not using comma, we are just writing H, K, L inside a bracket. Now, H, K and L inside a curly bracket will represent a family of planes. Always note that H, K and L with comma inside a bracket is point, but H, K, L just inside the bracket without comma is actually representing plane. So don't get confused with both. Now, before going to indicate Miller indices, let's discuss why we need Miller indices. Till now, we were discussing about crystalline materials, which means we have already learned its property, that is, they are anisotropic in property, which means they have direction dependent properties. So there itself you'll understand in those materials you will be having specific properties which is aligned in certain directions, or they might have special property in certain plane. So to represent those things they need these indices. That is why we exactly using Miller indices. So for certain property which is aligned in certain direction, you can just represent it using those Miller indices. Let's start with crystallographic directions. Cubic lattice. And now we are marking its directions X, Y and Z. Now first you need to have an origin. So suppose we are taking this as the origin, and if you want to represent certain point inside this lattice or crystal, then its directions with respect to this origin. That is what we are indicating through Miller index. So, crystallographic directions means writing the direction of a point in the crystal from the origin, which we are assumed. And we have already discussed that square brackets are used to write the directions. So whatever you are seeing, 3 indices which is inside a square bracket, then just understand that that is direction, because specifically they won't mention in questions. You have to identify that if you are getting 3 indices inside a square bracket, it is supposed to be direction. Let's go for some examples. Now consider a cube. So by convention, just imagine that here whatever examples we are discussing, we'll be representing the direction in a cube. So if usually question will comes with cube only, it will be very difficult if you go for highly complicated crystals systems, but we'll be representing cubes here. So many of the questions will come in cubes only. Inside this cube, first you have to imagine an origin. So suppose this is our origin, then we are representing a point along y, and the direction of this point can be marked like this. Now how we can represent this marked direction? That is what we are going to discuss. Now look into it, whether we have to move any distance in the x direction from the origin. No, there is no movement in the x direction. But if you look into y, you can see our direction is lying along the y direction. So for the x, we don't have any movement, so we are representing it with 0. And along y, you have a unit movement happen, so we are giving it 1. And along z also there is no movement happen, so that we are again giving it 0. Now we are giving it in a square bracket. So 0, 1, 0 inside the square bracket is actually representing the direction which have marked in this cubic lattice. Now let's go for another example. Example 2. Mark the direction 1, 1, 1. So first of all, as usual by convention, we already told we'll be assuming a cubic unit cell or a cubic lattice. So let's draw a cubic lattice and let's mark its directions x, y and z. So here they have given the direction. So the first one represents the movement in the x, and second one in the y, and third one in the z. Now our first step is considering the origin. So here we are marking the origin. Now we can have a 1 in the x, which means from the origin we are moving a unit distance in the x direction. So just assume that the lattice we have considered is having a unit distance in all the directions, so which means we are moving a unit distance in the x first. Then y is 1, which implies we are moving a 1 unit along the positive y direction. Again, z is also 1, which means you are moving a unit distance in the z direction again. So we are reaching at this point. Now if we draw a straight line from the origin to the point which we have reached right now, that straight line actually indicates the direction 1, 1, 1. So we are representing that direction as 1, 1, 1 in a square bracket. Let's go for example 3. Mark the direction 0, 1, 1. So as usual, consider the cubic lattice, then mark the direction x, y and z. Now they have given 0, 1, 1, have to mark. So this actually corresponds to x, y and z respectively. So x is equal to 0 means there is no displacement in the x direction, and y1 means a unit displacement in the y direction, which we can mark like this. Then from there again a unit displacement in the z direction. So we are marking it from there like this. So we are reaching at this point. Now we are drawing a straight line from our origin to the point which we have reached right now. So that direction actually implies 0, 1, 1. That is the direction of that back diagonal of back face. That is what we have drawn right now. From origin to that corner means it is the diagonal of back face. So that direction actually we can represent like 0, 1, 1 in a square bracket. Let's go for another example. Mark 0 to 0. Now, the first thing is you need to understand that 0 to 0 is actually similar or it's equal in direction of 0, 1, 0. So, here only the magnitude varies, the direction of both will be same. 0 to 0 in square bracket. If we are taking 2 outside, we can write it as 2. If you are taking out, it is 0, 1, 0. So actually we are plotting this 0, 1, 0 because direction is same for both of them. We took the scale factor outside and we are going to plot this. So as usual, as the first step, just consider the cubic lattice and mark its directions x, y and z according to your convenience. So if I am marking x as this, y as this and z as this. Now the second step is considering the origin. So if I am taking this as the origin O. Now look into it. Our direction 0, 1, 0. X is 0, Y is 1, Z is 0. So we are reaching this point. So the straight line from origin till there, this point is actually 0, 1, 0. This is equivalent to 0 to 0. The only magnitude varies, direction is same for both of them. Now another example, mark 2 bar 1, 2. So here you can see that there is a bar above the first number. So bar over the number implies that we are moving in the negative direction, which means it can be bar just implies it's negative. So since we are writing it inside a square bracket, it is assumed that we are moving in a negative direction. So if it's in the parenthesis, it's actually negative plane. So all those things we'll discuss later. So now it's like if we are seeing a bar over a number which is represented inside a square bracket, which means in that direction you are moving in the backward or it's negative. We are going to mark this direction. So as a first step, consider the cubic lattice and mark its direction like x, y and z. Now we are marking 2 bar 1, 2. So if you take the scale factor 2 outside, it is 1 bar 1 by 2, 1. So now we are going to plot this. So here if you see bar is over the number which is in the place of x, which means x we are moving in backward direction, y and z both are in positive direction. Now to draw this thing in an easy way, first thing you have to do is shift the origin based on the negative value which is provided. So here you have x. which is marked with a bar, which means you need to move negative direction along x. So shift the origin accordingly. So usually we used to mark the origin here, like the junction of both x, y, z we have marked. But since we have a negative in the x, so if we just move one step, 1 unit forward in the x direction and choose the origin. So this is our origin right now. Now from here we are going 1 unit backwards, that is 1 bar. Y is half. Let this be half in y direction, which is positive. So then from there we are going half distance along the y. Then z is again 1, which means from there we are moving 1 unit in the z direction again. So we have reached this point. Now, if you draw a straight line from our origin to that point, this line became curved, please don't mind it. So if you're taking the straight distance from origin to that point, that exactly shows the direction 2 bar 1 2, which is actually equivalent to 1 bar half 1. Now consider another example. Mark the direction 1 2 bar 1. So first step is scaling it. So if we take 2 outside, it is half 1 bar half. So consider the cubic lattice, then mark the directions. So we are marking it x, y and z. Now if you look, you can see that bar is there in the place of y. So which means you need to choose your origin, you need to shift your origin in the y direction a unit distance. So I am taking the origin unit distance in the y, which is this is our origin. Then from there I am marking. So a half in the x, which can be drawn like this. Then a negative 1. So from here we are moving in the negative y direction. So we'll reach here. Then a half in the z. Suppose this is half in the z. So we'll reach this point. Now the straight line from the origin till that point is actually representing the direction 1 2 bar 1. And this is equivalent to half 1 bar half. Now another question. Mark the direction 1 bar 2 bar 2. So as usual, consider the cubic lattice first. So we are drawing the cubic lattice and marking its directions x, y and z just like this. Then 1 bar, 2 bar, 2. So here we are taking the scale factor 2 outside. Then it's half bar, then 1 again. So half bar, 1 bar, again 1. So we are going to plot this. So how we'll choose the origin? That is the thing. So here usually we'll choose based on which one having the negative. So here what we'll do. So how we'll choose the origin. So here both x and y having bar. So for convenience, it's better choose y first. So we have to move a unit distance forward first in y and then again forward half distance in x. Then choose the origin. Which means usually we use the origin like from the junction. But now we are moving a unit distance in the y. But we have also bar at the x. So again we are moving a half distance in the x and we are reaching at this point. So choose this as our origin. So see, half distance we already moved in the x and 1 unit distance in y and we are choosing our origin. So now we are marking. So from our origin Now we are moving half backward, which means this is our x direction. So we are going backward half. So we are reaching here. Then a unit backward in the y. So now we reach there. Then a unit distance in the positive set. So we'll go and we'll reach here. So now we are drawing the straight distance from origin to the point we have reached. So this straight line actually representing the direction 1 bar, 2 bar, 2, which is equivalent to half bar, 1 bar and 1. You just yourself do some work like plot 1, 1 bar, 1. Similarly, try to draw 1 bar, 1, 0. I hope you all understand what is the method to draw all these things. So try yourself. You try other combinations also and practice this, how to draw the direction. Once you are clear with the directions, we'll go for the planes and all. So practice well. Family of directions. So initially we have studied certain notations, how we'll represent a point, how we represent plane, how we represent direction, everything. So if we have studied, family of direction is actually representing H, K, L inside angle brackets. So if you are seeing H, K, L values inside angle brackets, it implies it's a family of directions. So what it is exactly? Consider the directions 1, 0, 0, 0, 1, 0, 0, 0, 1, and also in the negative 1 bar, 0, 0, 0, 1 bar, 0, and 0, 0, 1 bar. So we have written 6 directions as a group. So what is similar here? So if we consider a cube like this, then if you're marking the directions x, y, and z, then 1, 0, 0 means this direction, 0, 1, 0 means this direction, and 0, 0, 1 is actually along the z direction. So if you consider any two such points, all those are equidistant. See, if you take the direction along y from the origin to that point, it is having a distance which is same as if you draw the same direction in the y, in the z, and similarly the same distance for 2 points in the x. So similarly in the back negative direction also. So if you mark any of these points, 1, 0, 0 or 0, 1, 0 or any points inside this group, you can see that the distance between the points which you have taken there is same. So all these are actually equidistant. So these all are representing a family. And we can represent this as, you can choose any of this. You can choose 1, 0, 0, 0, 1, 0. It's up to you. Choose any of them and write it in an angle bracket. So I'm writing it 1, 0, 0 inside an angle bracket, which actually represent the family of these 6 directions.